We've just started taking data again at the Large Hadron Collider with our experiment ATLAS and another experiment called CMS. And what we're looking for is a particle called the Higgs particle. Now, this Higgs particle is very important to our theories because it's the thing, if it exists, that we believe gives mass, gives weight to all of the elementary particles. We're really trying to ask and answer the questions, what are the fundamental particles? What are the fundamental forces? Namely, what are you and I made of? And that's a question that perhaps mankind has asked themselves for thousands of years. We have 3,000 physicists working on our experiment. We have 1,000 graduate students working on our experiment. And so, while I can't tell you what the discovery of the Higgs will mean for you tomorrow or for society tomorrow, I can almost assure you that in 20 years or 50 years from now, the basic research that we do now is going to be the engine that drives technology in the future. There is a relationship between astrophysics, for example, which is the study, let's say, of the universe as a whole on the large scale, and what we do, which is to look at the very smallest distance scales. But by looking at the very smallest distance scales and by probing nature at its very small scale, the way we get there is by putting together two particles, smashing them together at very high energies. And when you think about this, we're looking at phenomena that occur with very high energies. Well, that's the state that existed in the universe very early on in the universe. So the kinds of stuff that we're looking at, it's as if we're recreating the conditions of the Big Bang, or very shortly after the Big Bang. So in our case, about 1/10 of a second after the Big Bang is the kinds of conditions that occur in the collisions that we're studying. So again, our colleagues like Amber Miller, who study the cosmic microwave background, that's again looking at the universe at its very early stages. So we're both looking at the universe at a very early time, but we're doing it differently. We look at the very small, she looks at the very large. I think it carries on a long tradition that Columbia's had of leadership in physics, starting from the very early days from Michelson to Rabi. There's been a tremendous, rich physics history at Columbia, and particle physics, which changes with time. What is the energy frontier? It gets larger and larger energies as time goes on, but Columbia has always been at the energy frontier. And so I think this is carrying on that great tradition, and I think it offers an opportunity for students coming in, for graduate students, to be at the forefront of physics and learning these, and looking at the phenomena of the very small at the very largest energy scales. We're asking the big questions. I mean, the big questions are why are we here? How are we made? What's the stuff we're made of? As I say, these are questions that I think are fascinating. These are questions that interest people from 2 years old, asking the question why is the sky blue, why is nature the way it is, to people that are more expert and understand more of the physics that we're doing and find it fascinating. So I think I've noticed that it captures the imagination of people from very young to very old about these really fundamental questions.